So, for today's lesson, we are going to talk about vectors. And this particular section of chapter 5, which is 5.09, is all about vectors. All right. And we're going to first talk about vectors in terms of their component form. And so our focus for this lesson will mostly be on notation and pretty much the basics, okay? Just the basics of how to write the component form of a vector and so forth. So pay close attention to this. It's really a vocabulary notation and simple basics, all right? So the first thing is, what is a vector? Okay. So a vector, you could say, is a directed line segment. Okay. That's one way you could say it. So what's that mean geometrically? Geometrically, if you're on a graph and you see a line segment like this with an arrow at the end. So in other words, it has a direction, okay, and it has some sort of size, which we call magnitude. Then that directed line segment, that has direction and magnitude, is called a vector. Now, for a practical example, in the real world, scalars are things that are just a number, okay? But vectors are things that have the property of a scalar. They have some number associated with them, but then they also have a direction associated with them. And so here's what I mean. Suppose you have you drive your car and you go 40 miles per hour. Okay? That is considered a scalar. It's just a number. We're going 40 miles per hour. But if I say I'm going 40 miles per hour south, like that, then I consider this a vector because it has a direction. Now, the directions don't always have to be north and south. They just need to be an indicated direction by the particular quantity. So, for instance, if you start to think about physics, okay, physics, first of all, is where you have big applications of vectors, all right? In fact, almost all the quantities we deal with in physics are considered a vector. So a really common thing is, suppose you have an inclined plane and you have a box that is sliding down the plane, okay? Then that box has a weight and a direction that it's sliding. There's another vector, that this vector here represents friction. Okay, there's the box is resisting sliding down the plane for some reason, because there's a force pushing that box next to the plane, so it slides slower. There's some friction there, so that's a force. And then if the box is sliding down the plane, it's going in that direction, and there's some speed that causes it to slide. So this vector is sort of the sliding vector, and this vector, the friction vector, is sort of the resistance to sliding. right? And if you've seen anything slide down some sort of incline, like a child on a sled, all right, there's some resistance to that sled going downhill, which we try to mitigate with wax on the rails of the sled or certain kinds of sleds, all right? But you're still sliding. And then together, these vectors essentially create another vector, all right, which is sort of the sum of those two vectors, which tells us what the magnitude. Anyway, it's physics, and I'm not very good at explaining physics, so I don't want to go too far. But for those of you who've had physics in inclined planes, you've dealt with vectors. That's an example, all right? And all physics problems where you're studying motion and objects moving have some sort of number or speed associated with the movement, as well as a direction associated with that. And that then, those are vector quantities, okay? So this becomes a very practical thing. Now, we're not going to study how to do these problems. We're just going to study the mathematics of how you deal with vectors, okay? How you deal with them. All right, so let's go on. So we want to define this a little better mathematically. So let's talk about a geometric vector, and we'll start there. Okay, so in geometry, we talk about line segments, okay? So we have a coordinate plane, and if I give you 2 points, P and Q, then there's a line segment containing those 2 points, all right? In fact, you could say that there's a line containing those 2 points. And if we only consider those 2 points and all the points between, then that's a line segment. So we often talk about line PQ, all right, and line segment PQ in geometry. So when we start to talk about vectors, we talked about a directed line segment. And what we do is we label one of the points as the initial point and one of the points as the terminal point. And then this line segment becomes a directed line segment or a vector. Now, it's only this big. It's not a ray or anything like that. So in mathematics, when we talk about vectors, it looks like we're saying ray PQ like geometry, but this notation means vector PQ for us in this class, all right? And it's the directed distance from P to Q. And it'll have that length and it'll have that direction. And of course, if Q changes position, then PQ will have a different direction, all right? And we often say that our vector is equal to some directed line segment from P to Q, okay? And so, as you can see, here's single letter vector notation, here's 2-letter vector notation if we know the initial and terminal points. So that's notation. So there is such a thing as a zero vector, okay? That's just a vector that has no direction and no magnitude, okay? Or its magnitude is 0, all right? And so what we're going to do here is we're going to create a mathematics of vectors. It turns out they become things we can add, subtract, multiply, divide, and everything, okay? So we want to look at that, okay? Now, another thing that we say is 2 vectors are equal. 2 vectors are equal when they have the same magnitude and the same direction. So geometrically, here's a vector and here's a vector. Now notice they're in the same direction, and if they have the same magnitude, the same length, then those vectors are considered equal. So algebraically, we can represent a vector like this. We can say V is equal to AB. Now, what is A and B going to be? So if we look at it geometrically, if our vector starts at the origin and ends up at a point out here, and that point has coordinates AB, then that is the component form of the vector. Now, I want you to notice the notation. We always put the arrow over a single letter, but if we write a vector in component form, we don't use parentheses, we use these chevrons. They call them chevrons. Chevron parentheses to represent a vector, okay? Now, A and B are just real numbers, and so if we draw this vector, then this vector is in component form, okay? And A and B are just numbers, they're scalars, okay? And then, of course, we want to then be able to work with that. If a vector is at the origin, all right, its initial point is the origin, then we call that vector a position vector. Okay? We call it a position vector. All right? Now, if you have a vector whose initial point initial point is not the origin, and so we've drawn several vectors earlier, but you can have a vector that looks like this. Its initial point is not the origin. So in other words, it'll have ordered pairs here, some ordered pair here, A, B, and some ordered pair here, X, Y. And what we'd like to do is we'd like to find the position vector that's associated with this vector. In other words, it has the same magnitude and direction. So we'd like to find this vector. All right? Well, how do we do that? Well, all we have to do is take the initial and terminal point, and you take the terminal point value, x, and you subtract a. All right? So you take the x coordinates in their initial and terminal points and subtract them. And make sure it's always the terminal minus the initial. So you always want to think terminal minus initial, okay? And then y minus b. And if we do that, this vector right here is going to be our position vector, which has the same magnitude and direction. And its terminal point coordinates are going to be x minus a, y minus b. And the initial point will be the origin, okay? And so this is how we can find a component form of a vector anywhere in the plane. And we can find the position vector for any vector, all right? So what that leads us to then is a couple of types of problems that we want to be able to do. So let's do that on the next page. So the kinds of problems that you're going to have are going to be this. You're going to see a graph. So this is number one. You're going to see a graph of a vector. All right. And they want the component form of the vector. Okay. Essentially, they want this will be a position vector that you're writing its component form. So for instance, the problem will look like this. Okay. Okay. So here's a vector, and I see the initial point is 0, 0, and this is the terminal point. So the vector that I would write would be 4, that's the component in the x direction, and then -2. So I would essentially just write the terminal ordered pairs, but then it's a vector, so I would put it in vector notation. Okay? Any question with that? That's the first type of problem that you do. All right, let's go to problem 2. So problem 2, they do the same thing. They want you to write the component form of the vector, but this time the vector is not in it's not at the origin. So in this case, you would take the terminal side. Terminal point is 3, 0, and the initial point is 0, -2, and then the component form would be the terminal minus the initial, remember, 3 minus 0, and then 0 minus -2, and that would equal then 3, 2, and so the actual vector, the component form of the vector, position vector, would be this one right here. Okay? And that would be that problem. All right? So they do it first from graphs. So then what they do at that point is they will give it to you in terms of ordered pairs. So the third type of problem that you'll get is they'll say, oh, the initial point is -2, 7, and the terminal point is 3, 1. All right. And so the component form of that vector, essentially what is the position vector that corresponds to this vector with these points, would be always terminal minus initial. So it's 3 minus a -2, and then 1 minus 7. And that is equal to 3 plus 2, 5, -6. And this would be your answer in that case. Okay? Now, those are the basic problems that you are asked. Okay? Now, there are a couple others that you are asked, and so we want to look at those just briefly and see what the similarities are. So, the first thing that they do is they do vectors in 3 dimensions. And so, I don't know if you remember doing this, but I would print some graph paper because it makes it helpful to do that, makes it neat. And you can print nice square graph paper that you can draw 3D graphs on in Compotech.com or mathbits.com. And so you can get some good graph papers to be able to do that. All right. So what's the vectors in 3D going to look like? Well, first of all, just a brief review of 3D. If you remember, we normally have the XY coordinate system. So what we do is we drop that down flat so that this becomes the y-axis going across, and the x-axis visually is coming across like that. And then what we do is we put a third dimension, the height. So I always say think of the corner of a room, okay? And I probably should have drawn this as a dotted line. If you think of the corner of a room, that's up or down, that's what you're kind of looking at for 3-dimensional. Now, to put an ordered triple, say 2, 1, 4, like that, you would come out 1, 2. You'd come out 1, 2 in the x direction, and then you would go this length in the y direction. And so one way to see that is you can dotted line it. So you'd be there, and then you would go up 4. So 1, 2, 3, 4. That would end up right about here. All right. Now, the key thing with this is really 3-dimensional. Okay. And this point is the front of the corner of a box. All right. And if you draw it in, you can see it. And there's the point that we want. So we go 2, 1, and then 4. 2, 1, 4. And that's the front corner of a box on the top of the box. All right. I'll show you this a little more in class if we need to do it, but you can look up some 3D graphing. Now, the easiest way to think about it is what you're doing is you're taking the point 2, 0, 0, 0, 1, 0, and 0, 0, 4, and you're graphing those. So what are those? So 2, 0, 0 is this point, and 0, 1, 0 is this point, and 0, 0, 4 is this point. So if you look at that from those points, you can create the box and find the point that you're looking for. There will always be a corner of the box. Okay? So that's kind of 3-dimension graphing. Now, it's very analogous. If this was in space, if you have a point out on the graph, then the vector will be the line directed line segment from the origin to that point. Now this one's on the axis, so it's kind of hard to see that it's shooting out towards us, but it's from the back corner of the box, which is the origin, out to this point. Okay, so it's a diagonal of the whole box. All right. And since this point is connected component-wise, you can rewrite this as a three-dimensional vector as well. Okay? 2, 1, 4. Now, all the component, initial, and terminal side stuff applies to 3 dimensions. So I just wanted to go over what it was like to graph it, but in terms of doing the problems, you're going to do exactly the things we did here, except you'll have 3 coordinates. Okay? I do want to go over one problem and I'll set it up. So I took a moment to draw this as neatly as possible. Suppose I was looking at a picture like this, and I want to list the component form of this vector. So I'm doing this graphically. What would I do here? What's going on? Well, what I see is here's the initial side down here, right? And here's the terminal side. Now, I see that this box, the x value goes backwards, so it's negative, and it is -3 there. I see that the y value goes to its positive side, and it's a +3 here. And I see that the z value goes up, and it's a +3 there. Okay? So what would this point be right here? Well, it goes -3 back, then it goes 3 to the right and 3 up. So watch this as I point with the lightsaber. So, or right here, we start here, we go 3 back, 3 to the right, 3 up. Okay? X, Y, Z. All right? And so this vector is -3, 3, 3. Okay? And you want to be able to follow through that. Now, here's the trick. Sometimes people will look and they'll go, hey, that y value's at like 5. But you can't do that. You've got to follow the contours and where it comes from sort of diagonally, because you're looking at this as 3 dimensions. And early video games did dimensionality like this. Some of the early 3-dimensional video games. Gosh, I wish I could remember what they were. They came out when I was in college, like 1983. So all the games were super popular, you know, Galaga, Asteroids, Defender, Joust. Those were all really popular, but they were basically 2-dimensional. And then a game came out that had this kind of 3-dimensionality to it and kind of changed the whole world as far as games go. Anyway, that's the kind of thing you want to look at. All right? So that's all I have for you. Good luck on this first unit, and I will see you later. Bye-bye.